All right, so let's talk about the difference between exposure and air karma. These terms can kind of get misconstrued. Exposure, remember, is a unit. It is a unit that we express in. So don't think of it like you're making an exposure. It has a double meaning, the word exposure in radiography, as well as contrast. So when we talk about contrast, we can talk about actual detail on the film, or we can talk about contrast that we ingest, right? Two separate things. So when we say we make an exposure, it's not the same thing as saying we are measuring exposure, okay? Measuring exposure is different than just exposing. So it's an actual measurement and a tool and a device that we're going to use to measure something. So the definition, when a volume of air is irradiated with X-rays or with gamma rays, the interaction that occurs between the radiation and neutral atoms in the air causes some electrons to be liberated from those air atoms as they are ionized. So ionizations in air. We're on page 64. Ionizations in air. It also tells you that as the intensity of the X-ray exposure of the air volume increases, the number of the electron ion pairs increase. So exposure, I want you to relate it to ionization in the air. Ionization in the air. Okay. It also gives you a definition with the actual symbol. I know we've talked about it a little bit already. It's defined as the total electrical charge of one sign, either all plus or all minus, per unit mass that X-ray or gamma rays, X-ray or gamma ray photons with energies up to 3 million MeV generate in dry air. So to actually measure ionizations, you have to have what's called an ionization chamber. An ionization chamber. And they kind of go into detail. It tells you that it is a radiation quantity that expresses the intensity of radiation delivered to a specific area, such as the surface of the body. So when we talk about exposure as a dose, it is more of a skin dose, so it's not deep, right? So we're not talking about anything that's penetrating inside of tissues. Exposure is in the air. The air obviously touches our skin, so it's an estimation of exposure that is reaching our skin, all right? Ionizations in the air. So when the X-ray passes through the air, it's interacting with the actual air atoms, and electrons may be ionized, pushing out electrons, right? Everybody feel good with that? It tells you also that you can measure it using an accredited dosimetry calibration library, an ADCL. You definitely want to know what that is. It's a specific lab where we can use free air ionization or standard chambers to actually measure exposure. So we can't just go in with some kind of clocking device or some kind of Geiger Mueller or any kind of radiation detection device, any kind of dosimeter, and measure exposure. We have to have some kind of chamber that takes the air, pulls it in, changes the temperature, changes the humidity, and measures ionizations within the air. So it's a specific device. It's called a free or a standard ionization chamber. And we're going to talk about it today when we talk about measurement devices. Measurement devices. All right, so let's turn the page, still talking about exposure on page 66. So the coulomb, noted as C, is the basic unit of electrical charge. So it is equal to the amount of electrical charge moving past a point in a conductor in 1 second, when an electrical current is amounting to 1 amp. So amp measures what? What does amp measure? Do you guys remember from Physics 1? Current, flow, good. Essentially, the amp quantifies the flow of the electric rate. So the flow of electrons, So 1 coulomb, you could say, equals 1 amp in a current. 1 coulomb equals 1 amp in a current. So coulomb is going to be your SI unit, or your IS number, sometimes referred to. So it's a new international unit that we use. Yeah. It's a new international unit. So coulomb is not a traditional unit. Remember traditional rad, rem? We aren't using those these days as much, even though we do have dosimetry reports written in them still in the US. We try to focus more on those IS or SI numbers. So coulomb per kilogram, you want to know that one. They do not change it yet for the actual registry, so you might see it noted as coulomb or coulomb per kilogram. It's the same thing. So coulomb is the same as coulomb per kilogram. It will change within the next few years once they do more documentation and kind of measurements. But for now, that's all you need to know. So this exposure unit is simply equal to an electrical charge of 1 coulomb produced in a kilogram of dry air by ionizing radiation. Remember, when we talk about exposure, the air must be dry. The air must be contained in a chamber for us to be able to note it. So a coulomb is going to be expressed as equal to an electrical charge produced in 1 kilogram of dry air. So basically, they're weighting the air and seeing how much charge is in it. But remember, this is all done within an ionization chamber. It has to be secure. So think of it in terms of an x-ray tube and producing x-rays. If we don't have a vacuum, we have no x-rays. If we don't have the ionization chamber to actually dry the air, change the temperature, change the humidity, we can't measure the exposure. Everybody feel good with that? Okay. So exposure, ionizations, and air. Now we're going to talk about something called air kerma. Air kerma. So it is an acronym. They note it in different ways. I don't know why they call it kerma when there's really no M in the definition. It's in the second paragraph. It's kinetic energy released in air, or it could be noted as kinetic energy released in material, or kinetic energy released per unit of mass. So kinetic energy released in air is basically our foundation there. It's an SI unit that is used to express how energy is transferred from the beam of radiation to a material such as the patient's skin. So air kerma is kind of what we're shifting to from exposure. It is more accurate because we're not measuring ionizations, but we're measuring energy, right? So we're not measuring ionizations like exposure, we're measuring energy. So it's more accurate of how it's actually going to interact with our skin, with our body, with our tissue, how biological damage is actually occurring. So we should shift to this pretty soon. You will see both. Did we talk about this already? What are you guys seeing on the actual fluoro units? Are you guys seeing air kerma, or are you seeing exposure? What is it?
So DAP.
Okay, DAP, okay. So they're seeing DAP. Everybody's seeing DAP on a fluoro unit, dose area product. So it kind of pairs that with air kerma. That's new terminology. So if you see that on your machine, it's probably newer, not ancient, right? It's good that we are moving into better equipment, because as we get more efficient in our equipment, we decrease our dose, have higher image quality, and we're able to radiate more deeply without damaging cells. So we're able to actually achieve better imaging without hurting the patient or damaging tissue. So it says modern radiographic and fluoroscopy units have incorporated an ability to determine the entire amount of energy delivered to the patient by the X-ray beam. This is referred to as the DAP, the dose area product. Dose area product. I want to highlight this one. It's for sure going to be on your registry. It is essentially the sum of the air kerma over the exposed area of the patient's surface, or in other words, a measure of the amount of radiant energy that has been thrust into a portion of the person's body or the patient's body. It is measured in milligray per centimeter. So milligray per centimeter. You definitely want to know that. Highlight that one. Milligray per centimeter. DAP. So the amount of exposure in the surface that is potentially going to push into the person's body. So we're using air kerma to determine this because then it is the new or the more efficient way to measure exposure. So remember, exposure, ionizations in air, air kerma, kinetic energy released in air. Kinetic energy released in air. So more applicable for what it's actually going to do to the body. Our body is not composed of air, right? We have a lot of different tissues. So we want to know more of what the energy is going to do within a tissue structure rather than what the exposure is going to do to the air. The only thing that we have air in our body is what? Our lungs, right? So that does not compose the majority of our body. The majority of our body is water, it is tissue, organs, structure, bones. So that's a more realistic aspect of what it's actually going to do. That's why we use air kerma and why we want to use air kerma, if the machine has the ability to show us that. So what do you guys record as far as fluoro time? Do you record the DAP?
Yes.
Yes. Okay. You record the DAP and you record the time?
Yeah.
Okay. Okay, good. I like it. Okay, it also talks about absorbed dose. We already talked about that on page 67. Absorbed dose indicates the energy that the patient actually receives from the exposure to the ionizing radiation. Remember, absorbed dose can be noted as D, abbreviated as D, and it's measured in what? Gray. Good. Absorbed dose is gray. Good, good. All right. We are going to skip over the effective dose and equivalent dose because we did talk about those last time. You guys did good on your homework. On page 71, if you do decide to read through this chapter in detail, I would not read about a collective effective dose or total effective dose equivalent, so Teddy or Cole effective, because these two are not on your registry. So we're not going to do any math for them. We don't need to know how to calculate them. We're not medical physicists, and we don't need them for our registry. So if you decide to read through this chapter, page 71, collective effective dose, and Teddy is not on the registry. So you do not need to know how to calculate them. All right, so let's go into radiation monitoring on page 76, radiation monitoring. So I'm going to go over the very beginning portion of this chapter, and then I'm going to group you guys up so you can teach me about the different types of dosimeters. I know you guys love it. You love it. All right, so let's talk about it. Page 76, personnel dosimetry. It refers to the monitoring of equivalent dose to any person occupationally exposed on a regular basis to ionizing radiation. So it is required to have a dosimeter or some kind of monitoring device whenever a radiation worker is receiving 10% or more of the annual occupational effective dose limit, which is 50 millisieverts. You want to know that for your registry. 50 millisieverts. It measures it in 5 rem. You don't need to know the rem amount. Remember, we don't use those traditional units for registry purposes. Only in America do we get those on our dosimetry reports. So we need to know the effective dose for the occupational annual limit is 50 millisieverts. So if you receive 50 millisieverts, you are done for the year, right? It doesn't matter if we write a letter to Landauer and say her badge was in a fluoro room or in a special procedures suite or in some kind of cardiac cath lab for 7 days and she wasn't actually in there. We can't prove it, so they will not take our word for it. So they will send you back a letter in the mail that says your quarter dosimeter for Landauer has expended your effective dose for the year over 50 millisieverts. You cannot work for the rest of the year, right? So pay attention to where your dosimeter is. If you lose it and you don't tell someone you lost it, when they do find it and they throw it back to Landauer in the bag, they will read it and say you are over your dose. So if you lose your dosimeter, that's why it's important that you tell somebody that you're working with, because somebody will just put it where everyone else's are, right? So I had one person that this happened to. She said that she lost it, but she forgot to report it. Somebody put it in the drop box to go back to Landauer, and she couldn't work for like 6 months. So no one would hire her. She couldn't get any kind of a traveling job because once they submit your name to Landauer, it'll say, it's not safe for you to work in occupational radiation for the year, right? So just be careful. Just something to take note of. Probably not going to happen to you though, right? So it does tell you that here in America, if a healthcare facility thinks that you might receive 1% of your annual occupational effective dose limit in any month, they will typically assign you a dosimeter. Remember, the requirement is if you're receiving 10% or more of your annual dose. So if they think you would receive potentially 10% or more, you're going to be wearing a dosimeter. Most places are more cautious than that though. Even dental offices, they have dosimeters. If you've ever seen like assistants or hygienists wearing actual dosimeters, they don't receive 10% at all, maybe like 3%. But if you do go to the dentist and they want to x-ray you, make sure you ask for protective gear, right? Anybody ever been offered protective gear or not offered protective gear, right? Any kind of lead.
Yeah.
Offered, yes, no. They put it on you, okay, all right. Maybe my dentist is just slack. I feel like they never shield me. I feel like I'm always the person that's like, can I have some lead? And they're like, oh, the dose is so little. I'm like, I worked in x-ray for 10 years. Like, I don't want any more dose. I'm like, do you know what dose does to your body? And the hygienist is looking at me like I'm crazy, but that's another story. But if you do get any type of radiation, you want to make sure that you protect yourself aside from your occupational dose, because you will probably be working with this for a period of a length of time, right? You plan on making this a career in some aspect, so be cautious of your actual intake, right? So routine placement of dosimeters. So based on your dosimeter, it will assign you an effective dose on where it's located. So everybody should have a dosimeter in this room. Maybe you don't have it with you. I'm wearing mine. Mine says it should be worn at the chest or the thyroid level. They also have some where you can wear at the head or some that you can wear at the neck. The consistency of where you wear your dosimeter is very important, because where we are wearing this will determine our effective dose. So remember, how they scan and run these actual dosimeters are based on a reading of where they are located. So if I'm supposed to wear this on my thyroid, I want this to be an actual representation of what my thyroid is receiving. If I wear it down here, it's not going to be that, right? I could be receiving much more dose here. Most people's waist is level with the actual fluoride table, probably not mine, it's under. But if you would receive a lot of dose to this, it might actually be higher than what your thyroid is actually receiving. Same thing as if you get a dosimeter for your head. I've never seen one of those, but if you got one for your head, it would probably be for brain sensitivity. Obviously the skull is not very radiosensitive, it's a bone, but your actual brain is, maybe your eyes, if they want to determine if you're going to get cataracts or something. So you want to make sure wherever your dot is on your dosimeter is where you're actually wearing it. It will show you a little man on the side, and mine says chest or thyroid level. So that's where you should actually be wearing it. So remember, don't do what I'm doing. But I'm not an x-ray right now, right? So if we ever make exposures in this class, I'll wear my dosimeter properly. Okay, it also talks about where you should wear your dosimeter. Hopefully you know this by now since you're almost to the end of the program. So where should you wear it in terms of fluoroscopy or surgery?
Outside.
Good, outside the lead. So wear it outside of the lead. Why? Why should you wear it outside the lead?
Is blocking.
The lead is blocking, potentially, right? The lead is blocking potentially. So lead can have cracks in it. You guys know they're probably on your case about hanging your lead up, not crunching it, not wrinkling it. However, if we miss something and there is a crack in the lead, if you wore this under a good piece of lead and it shielded it, but you had cracks or exposures or holes, or if you weren't wearing any shielding on your thyroid but you were on your chest, we want a more accurate depiction. So over the lead. Unless you are pregnant, then you want to wear this under. So if you do get pregnant when you're in the field, you want to wear this under. You'll get a baby dosimeter badge for a fetal dose, and you will wear it under the lead to receive an actual dose for your baby. So usually it's worn at the belly level, and it's just so that we can determine how much radiation the embryo fetus is receiving. It also tells you under when a protective apron is worn. It is important that you wear it outside of the collar on the anterior surface of the body, because the unprotected head, neck, and lenses of the eye receive 10 to 20 times more exposure than the protected trunk. So your head, your eyes, and your neck, if you aren't wearing lead on them, are going to receive 10 to 20 times more exposure than your actual trunk that is shielded by an apron. So that's why it's so important that you're wearing lead. So important. Remember, even though I've been teaching this for a few years, I can tell you when I was out in the field, there are a lot of people who didn't wear lead, or people who decided to go into interventional or specials and they don't wear the glasses. They end up getting cataracts. We don't know the long-term effects of radiation yet, right? So we don't want to be on one of those videos that we're watching one day where we didn't know what we were doing, right? Just protect yourself. I know it's heavy. If you feel like your lead is too heavy in the facilities and you're going to end up working in an OR or some kind of specials environment, cardiac cath lab, I'm trying to think, like neuro OR, like 6-hour cases, things like that, invest in your own lead. Yes, it's expensive, but if it saves your back, saves your body, and allows you to do your job longer, it's probably worth it. So you can get different weights of lead to where you're still protected, but they are lighter. You can also get lighter lead composed into smaller areas, which is lighter. So I'm sure throughout the department you felt like different weights Like nobody wants to wear that blue one over there because it's super heavy and janky, and everybody wants to wear this nice thin one that's light that we make for the physicians. So if you do end up working somewhere in fluoro, I advise you, if your facility does not invest in your own lead for infection control, you can test your own lead every year so you know there's no cracks in it, you're protected. Some people like to wear the skirts and the 2 pieces. Sometimes that's more comfortable. Some people just like 1 piece so they don't lose it. Make sure that you're wearing a thyroid shield if you're in the OR or any kind of fluoro environment because you want to protect your thyroid. It's very radiosensitive, right? You need all of those functioning organs to feel good. So don't let them die from radiation because that's actually what's happening, right? Over time, if we expose, we're killing tissue, right? So it's not good to be in long-term relation with radiation directly. It does tell you on page 77 that you can wear a second monitor. You can wear a second monitor when a protective apron is being worn. So if you do end up working in interventional fluoroscopy, an example would be cardiac cath lab. Anybody been into cardiac cath lab? Anybody ever seen it? Yes-ish, no. How about specials? Anybody go into specials or get to see any kind of special procedures? See the specials department? So in these areas, you are usually there to almost assist the surgeon like a surgical tech. So think of it like an OR environment, but you are right there with the surgeon. So if they need catheters or guide wires or stirrups or some type of NICE or dilators, you're going to be there handing the surgeon that, right? So you'll actually get the equipment ready. It's usually a flat panel detector C-arm. So versus the big II, I don't even know what you guys are working with out there. I haven't been in an OR environment in a couple years because of COVID. So when you see your C-arm, is it a big circle on the top or is it more of a flat square? Circle. Okay, so circle is more of an old school technique. It's called an image intensifier, right? Hopefully you learned about that already. Image intensifier, when you see that big circular cone tube, that's an older type machine. The more expensive and more digitalized fluoro, or it's gonna be a flat panel detector. So it looks almost like a small rectangle. You will see it on some of the newer fluoro unit tables. So a flat panel detector C-arm, I've only seen one in Jacksonville. It was at Mayo. So I don't know if you guys are going to see one. I've heard that Memorial is going to get one though. So it's a flat panel detector C-arm. However, a lot of the units that you're working with in the rooms are flat panel detector fluoro rooms. So look at the top of your fluoro unit. If you see a big section that feeds up, it's an image intensifier. If you see kind of a flattened rectangle or square on the top of it, where you're actually moving the tube unit, it's going to be a flat panel detector. These rooms are very, very efficient. We utilize these in specials and in cardiac cath labs, procedures that are going to be really long in length. So in these cases, you know how to work the table, you know how to use all the buttons, you know how to fluoro, you know how to set up the radiation, how to let everybody up in the room. You're working directly with the surgeon to get the procedure done. Lots of emergency type situations, so you're going to be on call a lot. And you will receive a lot of dose because typically the surgeon is going to be using the foot pedal. So if you're working with a good radiologist or a good surgeon that uses pulse, right? He might be pulsing manually with his foot, moving back and forth. He might be using the pulse feature on the machine. If you use the pulse feature on the machine, know that it's not actually cine mode, that it's not actually a video. It's more of a flip book. So it's taking a lot of pictures quickly, and that actually utilizes less dose than actually videoing or using live fluoroscopy. It's called cine mode versus pulse mode. So in pulse mode, it's actually just taking a bunch of pictures very quickly. It can be grainy, not as good resolution. You might not be able to see as good, so depending on what type of environment you're in, if it's neuro and they really need to see a small lamina of a spine, they might tell you to stop pulsing. Or they might have a preference to where they don't pulse at all. However, pulsing really, really reduces dose. And if you're working with somebody who's pulsing with their foot too, I always appreciate working with people like that because that means that they're cautious of the radiation that they're actually using in the room. However, you might work with an old school radiologist. I know I used to work with one at downtown in specials for a little bit. His name was Dr. Maury. And every time I went in a special procedures room with him, his foot just stayed on the pedal. And I mean, we would receive like hours of radiation. So just be cautious of that. And if you decide that you do want to work in an environment like that, invest in your lead, invest in lead line glasses, protect yourself, right? Because we don't know the long-term effects yet. If you do end up working there, they might issue you a secondary radiation monitoring device such as a ring. I do have one upstairs, so I'm gonna bring it down so you guys can see it. Anybody ever seen a TLD ring? So some kind of ring that you wear. So usually if you work in an environment like cardiac cath lab where you receive a ton of dose, maybe you're handing things directly under x-ray to someone, or if you're holding a lot. So I wore one when I worked at Wolfson because I was holding children a lot with my hands. So they would measure the actual radiation that my fingers were receiving. It's just an additional device where you can get a more accurate reading of what you are receiving. They didn't care about my thyroid as much because I was further away. They cared about how much dose I was receiving on my hands because you're holding all the time.
Were your readings high on that?
No, it was never high. It was never high. Nope. Because the amount of radiation that we're using is so minuscule to what we used back in the day. We have these nice efficient machines now.
Especially the peds, they're pulsing.
Yes, we're pulsing in peds. Yes, we try to get parents to hold if we can. We try to get nurses to hold. So just remember, since you are going to be working in this field for a long time, anytime you can get someone else to hold without having to repeat the image, do it, right? They don't work occupationally in radiation. You do. So you are going to be holding a lot. But take advantage of those parents who say, I'll stay in the room with them and hold them, or I can help, or I can assist, or if a nurse wants to stay with a patient who's combative. Sure, let me get you some lead. I'll be the first to give somebody permission to hold. Remember, no one is allowed to make the exposure for you or press the button. So we can't ever have somebody else do that who is not a licensed technologist. So just keep that in your mind. Unless you're a student, you guys can press the button, right? You're practicing. All right, so an extremity dosimeter, that would be a TLD ring. It's called a thermoluminescent dosimeter. You guys are going to research that in just a minute. We are going to skip over the section on page 77 where it talks about different types of lead requirements. We will go over all of the requirements for the fluoro tower, for a thyroid shield, for an apron, for lead line glasses, for walls, primary barriers, secondary barriers in another chapter. So those are coming up. All right. So I want you guys to split up into 6 groups. I don't know how many people we have here today. I need one group that's a little larger because one of the sections is bigger. So one group that's a little larger, but 6 groups. 6 groups. So how many people do we have? 4, 5, 6, 7, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. We have 23 people. So how many? 6 groups. About 4-ish people. All right. Split up. Split up, guys. Group up. Unless you want me to group up. I mean, I can. 1, 2, 3, 4. 1, 2, 3, 4. Right.
We always do, just turn around.
Turn around. Okay. You guys are going to do OSL. OSL. Okay. OSL.
You want us to just share paper?
Sure. Yeah. You guys, I'll tell you later. Just a second. All right. All right, so they're going to talk about a pocket ionization chamber. Pocket ionization chamber.
It is used in high exposure areas like cardiac cath labs, and it is the most sensitive type of the personal dosimeters.
Good to know. It's the most sensitive. The pocket ionization chamber is the most sensitive, so it can detect the least amount of radiation.
Yeah. Before use, it needs to be charged in a special charging unit, and it has to be fully charged to its predetermined voltage before use.
Okay, so it needs to be charged before you can use it, which is a disadvantage because obviously at one point in your life you're going to forget to plug something in, right? All right, what else do we need to know?
How it works. It has 2 electrodes. One is positively charged, one is negatively charged.
Okay,
One of the
reminds you of
devices
what?
exposed.
Reminds you of what? It has 2 electrodes, so one positive and one negative, which could remind you of what? The X-ray tube. Good, good.
And when the device is exposed to gamma or X-ray radiation, the air surrounding the pre-charged central electrode, which is positive, becomes ionized. The negative ions in the air are attached to the positively charged center electrode, neutralizing some of the charge there. This has the effect of discharging the mechanism in direct proportion of the amount of radiation which it has been exposed.
Good. So it reads it. It is an air chamber, so it is airtight. When the X-ray or gamma radiation goes into it, it charges one of the nodes up, and that's how it reads it.
So the accuracy of it, as Graylin said, it's like really sensitive. So, but it's usually read on site, so you can read it right away. It's like a little pinhole. You can kind of look through it. The bad part of it is if it's not read each day, it can give like a really false high reading. So that's why you need to charge it.
So it has to be read every day, and the reading is immediate. So after you receive the dose, you can look right into it and see the reading. Pocket ionization chamber.
And it also, if it gets like a mechanical shock, it'll give like a false high reading too.
Right, so if it's like electrocuted or it receives any type of high voltage, it could give a false reading because it's electronics. So think of it like your cell phone. If it gets electrocuted or if you get shocked by lightning, you're not gonna be yourself, right?
And the RSO is in charge of keeping record of it.
Good, the RSO is in charge of keeping the record. Who is the RSO? What is that?
Radiation
Safety officer.
Radiation safety officer, good. Radiation safety officer, good. Nice job, guys, thank you. Thank you for that. All right, you guys aren't back yet.
Yeah, I went to the bathroom.
You guys aren't back yet either. Where is everybody? Okay, you guys go. They kind of got an easy one, so this is a shorter section.
All right, we have the proportional counter. It's not used in diagnostic. It's mainly used in a laboratory setting, and it detects alpha and beta radiation and small amounts of other types of low-level radioactive contamination.
Right, so we don't use this counter in diagnostics, so you won't ever see a proportional counter in any type of an X-ray room or a kind of lounge or control room. We only see it in laboratory settings. It's not for diagnostic use, and it picks up alpha and gamma. And it is a radiation detection device, not a dosimeter. So this is something that's going to be sitting somewhere or detecting radiation, not that's going to actually be tracking it on your person, if that makes sense. Anything else, Ashley?
Yeah, so it travels, it checks the air around an object. So it travels only a short distance in the air, so the operator of the counter must hold the unit probe close to the surface to be read, and the most accurate reading is to be up close to it.
Good.
The closer you hold the probe to the object, the more accurate of the reading you'll receive, and it does emit alpha radiation from the object.
And it works as a gaseous ionization.
Nice.
chamber.
It works as a gas ionization chamber. So the closer you are to the object that you're trying to measure, the more accurate it will be. But you don't want to be close to alpha and beta radiation, so you're going to be standing back probably when you're measuring it, and even within a lab setting, because these people are not wearing shielding devices. They're usually testing some kind of liquid or some type of consistency that they're going to give to a patient. So maybe I think like SPECT imaging, nuke med, radiopharmaceuticals, things like that. But these are all within a lab setting, so nothing you're going to actually see physically at any of our rad sites. Good, nice
You said
information.
it can be used in SPECT and RadBio, right?
Yes.
Sorry.
Nuke med, yep. SPECT and nuke med, yep. Nice. So not for diagnostic use. Important to know about the proportional counter. All right, how about you guys? Tell us about this OSL.
So we did optically stimulated luminescence dosimeter. It's the most common in like occupational doses and stuff like that.
Okay.
It has 3 different filters: aluminum, tin, and copper.
Want to know those filters: aluminum, tin, and copper.
And each of the filters blocks out portions of the radiation-sensitive aluminum oxide.
Good.
There's like 6 different steps. First, it's like deposited into the electrons from the valence bond to the conduction band.
Mm-hmm.
And then they move into the traps of the bands. And then the greater the radiation energy absorbed dose is the greater number of trapped electrons. And then when it comes time to assess the dose, the trapped electrons are freed by exposing the dosimeter to light.
Nice. Exposing it to light, so luminescence, that's a word in the actual definition. So optically stimulated luminescent dosimeter.
And then when they're free, they fall to a lower energy level and emit light photons. And then the intensity is measured and used to calculate the dose.
Nice. Did they give you any kind of a reading, like when you can use it?
That's my part.
Okay.
So for the reading, the readout is by using laser light at selected frequencies. When such laser light is incident on the sensing material, it becomes luminescent in proportion to the amount of radiation exposure received.
Okay.
It's important to record it accurately to meet state and federal regulations. The minimal reporting levels, it said it was recorded in microsieverts or
Okay.
MRAM.
Okay, milliram, yeah.
So if you look on page, it's a list of them.
Oh, okay, okay.
So I'll just show you. It's on page 80 of the white book.
Okay.
It says like what the measurement is for the minimal reporting levels for X-ray, gamma, beta, neutron, fetal, and rings.
Nice.
I'm not gonna read all the numbers, but you can just look at it.
Oh, it's not, you give them that.
So the minimal reporting levels. And then it said the capital letter M, if you read it in the paragraph right above,
Mm-hmm.
it signifies equivalent dose below minimum measurable radiation quantity. And then if you look at this big chart on page 81,
Dosimetry report.
yeah, not the first, well, I guess you can look at the whole thing, but I look at the second one because I feel like it's easier to read.
Okay.
It records deep dose equivalent, eye dose equivalent to lens of the eye, shallow dose equivalent to the whole body, shallow dose equivalent to max extremities,
Mm-hmm.
and then the committed dose equivalent, maximally exposed organ.
Nice, nice. So this, when she's talking about the laser is going to read out varying energies subjected to the badge, sometimes they refer to that as a glow curve. So if you ever see the word glow curve, you can associate it with an OSLD. It is what they actually track the radiation with. So think of like a chart, almost like a bell curve, but think of it, it's called a glow curve. How bright is the object emitting light? If it is emitting a lot, there's a lot of radiation that it was exposed to. If it's only emitting a little, the glow curve is going to be low, not showing or demonstrating that much. It can yield readings as low as 1 millirem. You want to know that. It can detect as low as 1 millirem. And like they already said, it utilizes an aluminum oxide detector. The laser light reads the sensing materials, which causes the material to become luminescent in proportion to the exposure that the sensing material is received. The filters you want to know for this one for sure: tin, copper, aluminum. So as the radiation passes through these different filters, it is filtered out. If it receives dose through all of them, they would consider it a deep dose. If it only penetrates one, it's a shallow dose. If it penetrates two, sometimes they determine it as an eye dose or an ocular dose. So that's how they determine how deep the radiation actually went through the OSL.
Then we
Good.
have, advantages and disadvantages.
Yes, tell us. Go ahead and tell us.
Lightweight and durable, it comes in that preloaded packet, it's got the color coding and graphic symbols so you know where to wear it. It's tamper proof, isn't affected by heat, moisture, or pressure. And it's practical for employees and pregnant people. Disadvantages are unless you have an in-house reader, you can't immediately determine the dose of the day an incident occurs, and it only records in the body area in which you're wearing it.
Okay.
You have to wear it for it to work.
Good. So it only records where you actually wear it. So if you're supposed to wear it on your chest, it only records what you would receive to your chest. If you're supposed to wear it on your stomach, it only records what is in your stomach, right? So it is effective dose is what I would note it as, because it's taking into account the type of radiation and the tissue that's being irradiated. Good, good.
I read a little bit about the control badge.
Okay.
So the monitoring company will provide control badge, and this should be located in a radiation-free zone. And then if the reading does record above 0, they say it was exposed in transit, so usually they will subtract that dose from each badge that was in the bag.
Good, exactly. So every time I get your dosimeters, I get a control badge with them. They stay in my office here, away from radiation, within a normal background. So it might receive, I don't know, some kind of solar radiation, some kind of background radiation from maybe the computer that I'm working with or something like that. That's kind of your baseline. So that's what they use. And then we subtract that from what you guys actually received to note the actual dose that you received at the clinical site or on your job site. So the device that you are wearing is called an OSLD, also known as a film badge. So back in the day, they called them film badges because they actually had film in them. So they would expose these to a light, just like they do with the OSLDs. But when they specifically call it a film badge, when they refer to exposing it to the light, the film is actually developed, just like a film would be if we used X-ray back in the day. So how penetrating the X-ray would go through the film would determine how much you actually received. So these OSLDs are way more accurate. That's why we use them today. They used to be called film badges though. They used to be called film badges. So which type do we use on a daily basis? The OSLD. OSLD. Good, good. I can't think of anything else we need to talk about. On your dosimetry report, you will see a deep, a shallow, and an eye exposure within the 3 filters that are within this. If the radiation penetrates through all of the filters, that's how we get the different dosages. So deep versus shallow versus ocular or eye dose. And you will see this. Have you guys ever signed a dosimetry report?
No.
No? Okay. How many badges have you turned in?
4.
Okay. All right. So I probably have some somewhere in my office for you to sign before you graduate. You're supposed to sign it every time it comes back, so.
We've never seen them.
Okay, I'll show you guys some. There's somewhere in there, I'm sure, within the piles and piles of stuff. So I'll try to find them for you, but when you guys turn these in December, before you go on winter break, when you come back in January, you'll already have your new ones. Sometime in February, they'll probably send me a report of the readings. So you guys can take a look at them, sign for your actual dosage. You'll do the same thing when you get a job and when you work somewhere. They'll print out dosimetry reports and you'll be required to sign them, acknowledge them from your RSO. So it'll kind of get you in the habit of that. All right, good. Good, good, good. How about you guys over here? Yes. What do you have? Do you have a dosimeter or a monitoring device or a field survey instrument?
We have the survey meter, the QD5.
Okay, the QD5.
So ionization chamber type survey meter, aka QD5s. They are a rate meter device that can measure X radiation, gamma, and can be used for beta radiation if equipped. It accurately is used to measure exposure rates from patients getting therapeutic doses of radioactive material, and is especially valuable for reporting the cumulative exposures received in radiation oncology treatment rooms.
Good.
It measures intensities ranging from 10 to several thousand microgray per hour. And I was just about to write this point. It has the ability also to measure a wide range of radiation exposures within a few seconds or over a broad exposure of radiation injury. So it's got, one of its advantages is that it can detect a wide range.
Good.
And then, however, it is a disadvantage disadvantage is that without adequate warm-up, it cannot accurately measure exposure rates produced by typical diagnostic procedures because the exposure times are too short. So it's not good for regular diagnostic.
Good. So we use it in therapy, right? We use it in therapy and to detect exposure rates for radioisotope storage facilities. So either one of those. So nuclear medicine in the storage facility or in some type of room with radiation therapy. Good. I like it. That's called the gas ionization chamber instrument, also known as the QD-PI. Not to be confused with the pocket dosimeter. So this is an actual device that we're using to detect radiation at a site, not a personnel monitoring device. So not something that you would actually wear on you, right? Good. Anything else? I think you guys covered everything. It is sensitive to a large range of exposures. My book says 0.1 millirem to 1 rad, or 1 rem if you convert it like that. What did your book say? As sensitive as 1 microgray? Or 0.1 microgray? What's the minimum dose?
And the 10 micro, it says 10, it's kind of weird, like,
10 micrograys?
Yeah.
Okay,
Yeah.
10 micrograys, so I would know that one. Mine probably just isn't updated yet with the new terms, but 10 micrograys. And it can detect a type of rate for a minute, an hour, or several thousand hours. So it's very versatile in how it can detect. It's not just like, oh, we're gonna shoot it and see how much radiation is present. We're gonna leave it there. We can set it for a timer to detect radiation as far as like 10 hours during the day until I come back tomorrow, or 24 hours, or 48 hours over the weekend. So however you wanna monitor it, it's very versatile in the use of it. Nice. All right, last group, you guys. TLD.
So,
Two groups, sorry.
It's also called the thermoluminescent dosimeter, or the RIM dosimeter, and it's got lithium fluoride crystals in it.
Good.
Catch the radiation and transmit electrons into impurities. Those impurities hold the electrons until it's sent in to be measured. They put the ring into heating element, and when it gets hot, it emits light. That light is measured and calculated, and that creates a glow curve as well.
Good.
And it's most similar to human tissue because it's actually, the radiation penetrates into the crystal much the same way that human tissue does.
Nice. So there's crystals, so just like X-ray or radiation would penetrate different types of soft tissue, organs in our body, the penetration levels are pretty similar to it actually exposing a body.
Would it be similar to the way DNR works? Does it scintillate?
The scintillator, yes, in a way, but it's not going to capture it for long-term use. Yes, yes. So the functional component is the lithium fluoride, like he said. Readings from the TLD are made by heating the lithium fluoride chip to a point of combustion. So once it explodes, then we can read it. If you want to break down the word, or maybe you've got a question, you can't figure out which dosimeter, it's a thermoluminescent dosimeter. So thermo, heat, luminescent, light. So we expose it to heat and light to read it. It's a thermoluminescent detector or dosimeter. So it's good for monitoring over extended periods of time, less prone to artifacts or false readings, more expensive than the OSL though. More expensive than the OSL. So I actually have a TLD in here that you can see. It looks cheaper. I don't think it looks as nice as the actual OSL, but it's actually more expensive based on the reading. You guys probably won't see these. I have one from when I worked at a state facility. So a lot of times, whatever vendor they end up partnering with, they don't change, so they probably didn't know any better. The hospitals that you guys will work with here in Jacksonville, or if you work at a larger city like Jacksonville, you'll always have an OSL. But this TLD is a little bit more accurate, but it is way, way more expensive. So you probably won't see these. Once the chip is heated, it is destroyed. So you can't reuse the lithium fluoride. So once they heat it up, it's combusted and they read the radiation readout, it's destroyed. So we have nothing of substance. So we can't reuse it in any aspect. These are a little bit more versatile. Once they read these, they just pop a new layer in, pop the filters in, and send them back, right? So they print your name on it. So even though they charge us so much money for these, they're just recycled, these OSL monitors. But Landauer has a market on it. So if you want a job when you graduate and you want to kind of be an entrepreneur, you should create a radiation reading or dosimetry company. So Landauer has some competition because right now they don't. They kind of monopolize this. So everybody has to use these if you want an OSL, which are the cheapest devices that you can use. So remember that if you want a job after. There is no archival record other than a written record of the findings of this TLD though. This OSL will monitor you on a permanent basis. So if your name changes, they will say, okay, Jasmine got married, so we want to change her name in the system. We have to report it to Landauer so that we can have a running log of it. These TLD monitors are not as accurate as far as tracking your occupational annual dose and your cumulative occupational dose. So as far as tracking you over the years, that's why we use the OSL. Once these are read out and recorded manually, if they lose the paper or if they lose the document, it's gone. These are read by a computer, so everything is tracked and documented. You can change the name, you have a number assigned to your name, so we can't just input a new dosimeter for you. Your numbers will travel you for your entire occupational career, which is good. You want to monitor your radiation.
Is the TLD more sensitive than the OSL?
Yes, the TLD is more sensitive because of the crystals. So there's actual crystals in this that are similar to body tissue, whereas this one just has a layer of filters. So penetrating through the layers to get different types of dosages, deep, shallow, ocular. Make sense? Good, good. All right, the last one, you guys.
Between deep and shallow?
What's the difference between deep and shallow? Shallow would be like a skin entrance exposure. Deep, more penetrating to the tissue.
Ocular is between the two?
Ocular is eye, yes. Yep. So they don't consider ocular deep or shallow because it is an external organ, but we do monitor it because your eyes are so sensitive to radiation. So that's kind of why they track it. You guys, what do you have?
So we have the GM survey meter. What this does, it serves as primary portable radiation survey instrument for airline and nuclear facilities. With the assessment of alpha particle emission, the unit is sensitive enough to detect individual particles or photons. Hence, it can be easy to detect any air and contaminated by radioactive material because the GM survey meter allows rapid monitoring and sequence causes. So it can be used in to locate a lost radioactive source or low radioactive contamination by using this audio mode. Maybe also be employed to scan radiation barriers for any shielding defects.
Nice.
The components, the GM survey meter has an audible sound system that alerts the operator to the presence of ionization radiation. Metal enclosed in a counter gas field tube or probe, which is the unit system to ionization chamber. When the shield is covering the component, the chamber is open, very low energy X radiation and beta and gamma rays radiation can be detected. Meter readings are usually obtained in
Millirankin or milliram?
Kilogram per hour.
Milliram per hour.
The disadvantages of the GM survey is not independent of energy of the incident photons. This means that photons of widely different energies can cause an instrument to respond quite differently. And in addition, the GM survey meter is likely to saturate or jam when it is placed in post high intensity radiation areas such as radiation therapy, thereby giving a false reading.
Good. So the GM meter or the Geiger-Müller meter, this is used more as like a handheld device. There's a picture on page 89 if you want to see what it would actually look like. If you end up going to New Med in your 5th rotation, when you're comped out, you will see one of these devices being used. They will use it if they spill something. So if they spill something like a radionucleotide or something that is radioactive, they will use it to test the bathroom after the person washes their hands, sometimes after they go pee, if they go to the patient bathroom. If you lose any type of radioactive material like radium or radon or anything that you could use in nuclear medicine, you can use this Geiger-Müller to detect it. However, if you put it in areas where there's high radiation being used, like a therapy suite, so some kind of radiation therapy suite, it will tap out on you because it can't read that much, right? So therapy uses really high doses, whereas when we use those radionucleotides or radioactive substances, they're usually pretty low because we're ingesting them or injecting them into a body. So you can kind of scan a room. It will alert you, kind of like a metal detector kind of thing. It won't get louder if the detection is more or lower. So the sound remains the same. So that's kind of the disadvantage. You don't know if you are responding to a huge dose of radiation or a small dose. Nice, nice. Thank you, guys. All right, I'm gonna pass these around if you wanna look at them. It's just a couple of different film badges. I also have, so I have 2 OSLs in here just for different sites. You guys know what they look like though. You wear one every day. I have a TLD that if you want to look at it, you can. It will pop open, but I don't think it will separate. But don't feel like you're going to break these. So if you want to open it up, feel free to do that. And then I also have a TLD ring. So if you've never seen a TLD ring, you can look at this one as well. Yeah. All right, for the next chapter in this book, it is the overview of the cell biology. I'm not going to tell you that it's not important for your registry, but I hope that you do know it based on your prereqs. So we will not be going over this chapter in class. I would recommend that you know the difference between meiosis and mitosis. You want to know the difference between meiosis and mitosis?
Take cell development, right?
So cell division. Yep, cell division. Yep, mitosis has some different phases depending on what phase you're in will determine how bad the reaction to the radiation could be. So if the cell is dividing, if it's hanging out, if it's parenting daughter cells, so things like that, those are called phases: prophase, metaphase, anaphase, telophase, and then interphase is kind of the just development cycle. You want to know the difference between those though. So if you need to review those from anatomy and physiology, I recommend that. For homework, I would like you to turn to page 108. So 108 gives you a summary of the cell components. It tells you each component: the cell membrane, the ER reticulum, the Golgi apparatus, mitochondria, lysosomes, ribosomes, centrosomes, nucleus, nucleolus, and DNA. I want you to create, for homework, your own analogy of the cell. So I'm going to give you one just as an example. I'm going to relate a cell to a city. So the cell membrane might be the walls of the city, right, to keep us in it. If I want to talk about vehicles, I might relate them to the Golgi apparatus because it hauls the freight. So it hauls the material around the cell. If I want to talk about the endoplasmic reticulum, I might say it's the interstate. So it's the highway in which everything travels. We'll have our garbage trucks, which are also known as the lysosomes. So create your own analogy. It can be a restaurant, it can be a city, it can be something fictional if you want it to be. So whatever is unique to you to where you can remember the parts and components of the cell. You must include all of the components on this list in your analogy. It doesn't have to be fancy. It can be pretty mainstream. I don't expect everyone to have their own idea, but try to make it unique and something that you can remember, especially if you need to refresh on the cell information.
So what's the key terms from chapter 6?
Table 6.1.
Page 108. 108, table 6.1. It's a purple chart, and it says summary of cell components. Is it different in a different book?
Yeah, it's page 120.
120 in the other book.
We have to explain the analogies too.
Yes, yes. So I just want to know that you know what the parts of the cell are, how they function. The registry is very kind of broad in this coverage. It just says cell division to include cell components. So that's meiosis, mitosis, and all of the parts of the cells. So that's why we're going to kind of keep it generic as well. But hopefully some of this will be a refresher from A&P. If it's not, and you need to get with me after, I'd be happy to do some tutoring or some one-on-one with you. But it is pretty to the point.
Are you draw a picture or just?
You can draw a picture if you want. You can draw a picture if you want and label it, or you can write it down, a list form, whatever you want to do. Yep.
When do you want this by?
This is due on Monday at 11:59 p.m. Monday at 11:59 p.m. Why are you laughing?
So the paper.
What is it?
The paper
Monday
and
too. Yes. Yes, your paper's due Monday as well. Did I create a link for that? Has anybody
Not yet.
uploaded it?
Yeah.
All right.
Under RadBio, right?
Yes.
You said no phases, like interphase, all that stuff?
Yes. Know the phases of mitosis.
Over here on this side.
Yes.
Are we,
I want you to know what is actually happening in them. So when you review meiosis versus mitosis, one is gonna be specific to germ cells, one is gonna be specific to tissue. So mitosis is the germ or the sex cells, and you need to know what's happening at each phase. So what's happening during interphase versus prophase, metaphase? Are they doubling, are they tripling, are they splitting? This is really important when we talk about cell biology and the interaction with the X-ray. So depending on when the X-ray actually strikes the body will depend on how much damage is occurring. So for instance, if we strike a cell that's going through prophase that hasn't split yet, it will not be as damaging as if we striked it during interphase when it has split. If we have daughter cells in telophase, it's going to be major damage because we have very unique tiny cells. So think about radiosensitivity as far as like babies. Obviously, we don't want to X-ray women who are pregnant, right? When we have undeveloped cells, so cells that don't know what they want to be yet, don't know what they're going to go to, don't know what part of the body they're going to function, right? So they're just little kids, right? They're immature cells. We call these stem cells in the body. So that's why it's really important that we don't radiate fetuses, because if we did, we could cause damage in their future development before they actually decide what they're gonna be when they grow up, right? So that's kind of the concept of it. All right, so let's go to our patho book.
What about the information at the beginning of chapter 6?
The information in the
Like
beginning
when
of
it
chapter
talks
6.
about lipids and carbs
Yeah, you got it.
and
Inorganic versus
96,
inanic?
like nucleic acids and lipids.
Yeah, I would know those.
know
I would.
everything?
Yeah. I would review those. At least the major classes of the organic compounds, as far as the proteins, the carbohydrates, the lipids, and the nucleic acids, the big ones.
So we're interrelating how radiation affects that.
So for your homework?
No, just in general.
Oh, yes. How radiation would affect it, yep, exactly. So we need to know basic composition of the cell. It has a really nice cell picture too on page 104. I like that picture.